about Jupiter. Okay, so we'll start with the eccentricity of the Jovian orbit in this video, where we also get to celebrate the diversity of Shumbafoot content. Okay, so we know the formula of eccentricity. It's there with the epsilon shown there, and then that epsilon is equal to 1 minus that expression in the brackets there, and you see that the gm, capital letter G and small letter m, are cancelled in both cases there, because we used usually we use the aphelion and the perihelion in astronomical units, if we know in the previous videos that we have produced. So in this case we have used the meters in meters, where you know it's the common unit, meters, for distance. Astronomical units is more for in astronomy, when you're doing astronomy or whatever that has to involve space, where we are dealing with very large values. But here we just decided let's use the other unit so that we get to understand the idea here. It's not about using astronomical units, but as long as the units cancel for the aphelion and the perihelion, then you can use the values. So we do that, and then we get our epsilon, which is the eccentricity, being 0.04866, which is approximately equal to 0.048723 significant figures, and that's our eccentricity for Jupiter. It's very less compared to the eccentricity of Mercury and the other eccentricities that we have looked at, but yeah, that's basically the eccentricity of Jupiter. Okay, now we move on to Jupiter's radius. Now if you read the notes at the bottom there, it says, according to resolution B5 of the International Astronomical Union, IAU, a planet should have a nearly round shape. Hence it suffices for us to use the equation of volume of a sphere to estimate the volume of Jupiter, and that volume will be 4/3 of pi multiplied by pi r cubed. But here we are looking for the radius. So what we are trying to do is to make r, which is the radius, in this formula as the subject of the formula, which is why you see on the other side of the screen, you see it says here is a way of computing the radius after rearranging the formula of the volume of a sphere or a planet. So we're trying to use that formula of a volume of a planet, because we already know what the volume is after some calculations. So now we're trying to use that volume to find the radius using this equation with all these terms. So it becomes r is equal to the cube root of 3/4 pi multiplied by the volume v, and that's what you see there, the cube root of 3/4 pi multiplied by 1.4313 by 10 to the power of 13, and that will be equal to 69,911, pardon me, 0.29615. yeah. But then we can also calculate the units using that same formula there. So we know the units for our volume will be in cubic kilometers. So what do we use to find the kilometers? We cube root, because we have to cube root the volume there with the constant. So we also have to cube root the unit, which is cubic kilometers, within cube root, and then we find kilometers, as you can see written there. Then that's how we get our 69,911 kilometers, correct to the nearest whole number. Yeah, we're going to be dealing with some large values, so bear with me. We are not going to be using decimals in this case for the radius. Now you are using the conditions and the same or the criteria in the resolution B5 of the International Astronomical Union. We can also estimate the surface area of Jupiter, because we know the surface area of a sphere is 4 pi r squared. So we can use that equation again to find what the surface area for Jupiter. And like we saw, we already calculated what r is, which is the radius, with the 69,911. And that's why you find it included there, 4 pi multiplied by 69,911.29 blah 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 squared. because it's r squared, so that's why it's that number squared multiplied by the constant 4 pi. And then we get 6.1419 blah 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 by 10 to the power of 10 square kilometers. We're going to be putting it in square kilometers because our 69,911 is in what? Kilometers, as we saw in the last slide where we calculated the units and we saw that it was what? Kilometers. So here it's going to be square kilometers. How do we find that square? Because it's r squared. So the same thing we did there where we use our formula to find the unit, we also do it here. So we have our kilometers and then we put the square because our radius is squared. So that's why we have square kilometers there. And that's through three significant figures, the 6.14 by 10 to the power of 10 square kilometers, correct to three significant figures for accuracy. So now let's move on to astronomical or geometric albedo. Okay, so for the Jovian geometric albedo, we are trying to say it's the ratio of the light received from the sun by Jupiter to the light that Jupiter reflects, or that it allows to bounce off the surface, that it doesn't absorb, but it allows to bounce off. If you get the sense of reflection, where light has to bounce off a surface. Yes. So we are trying to look at the ratio of the two. So as you can see in the definition, there's also a part where it says albedo values range from 0, which is pitch black. So we are saying all light is absorbed, to 1, which is perfect reflector. As we saw with Eris, the dwarf planet, when we calculated the albedo for Eris, it was like 0.99, very close to 1, which means it's very close to being a perfect reflector. So we want to see if Jupiter is also close to 1, which is being a perfect reflector. How much does it reflect? Is its surface able to reflect all the light that is going to receive from the sun? Would the observer be able to see all that light? Okay, so let's see if the geometric albedo for Jupiter is going to be very close to 1. We are hoping that it's going to be close to 1, since we can see some light. If you look at the diagram of Jupiter, it has a predominantly white surface, but there are also some brown and grayish and whatever color that you see there, which means some colors may be absorbed, unfortunately, but we are trying to see if it's going to reflect a lot. So if we look at the equation, or rather the formula of the geometric albedo, is written there on top there, where h is the absolute magnitude and d is the diameter of Jupiter in kilometers. In kilometers, take note. We then have to find the a, which is the geometric albedo, and we then plug in our values. We find that our h would be negative 9.395, which is not really what other sources say. If you look down there, you see in green, the h that was used by other sources was around negative 9.437 or 438. To get 0.538 is their geometric albedo. So you should also take note of that. If you can see where I made the mistake in my calculation, please just comment down below and we'll see where I went wrong. But let us continue. So if you see in that diagram, you see there is a DES, DOE and the like. All those, if you see it's OE and DES, it was supposed to be D, OJ and JS. Not E. Where there is E, there was supposed to be J, but we used E because of the Eris. If you look in the Eris video, the E represented Eris and the S would represent the sun, the O would represent the observer. So where there is E, just put J. So those distances are used to find the absolute magnitude, which is h. Yes, so that's why we need those distances. We also need to know those distances because they affect the distance which the light is going to travel, which shows the intensity and all that. That is factored in when looking at reflection of the light and how the observer is going to interpret the effect of the light being reflected. And then our D will be the diameter by the radius by 2, which is basically the diameter. That's why we say it's 69,911. That diameter, the radius that we calculated before, that's the one we put there. Then we say by 2 so that we get the diameter. And then we divide into that expression on top on the numerator, and then we get our answer there, and then we square that to get 0.517482016, which is approximately equal to 0.517, correct to three significant figures for accuracy. So the 0.517 is the geometric albedo, but we find that there is also the bond albedo and the other geometric albedo, which is around 0.538. because other sources, like I said aforementioned, H should be around negative 9.438 for you to get the value that they got, which the other sources got, or negative 9.437 between those two. So I think let's move on to the next segment. Now looking at the Jovian black body temperature, this black body temperature is explained in the Stefan-Boltzmann law, which is stated right below there on the bottom left corner there in blue, or light blue, sky blue, whatever you call it. So we find that the energy will be equal to sigma by T to the power of 4, and that energy is what we call the energy radiated per unit surface area of a black body, which in this case is Jupiter. We have what we call the gray body and all those. It depends on what you're looking at in terms of the energy and all that. There is a certain definition of the black body that you can look at to understand why we have these different types of bodies in terms of energy. So our sigma would then be the constant, which is called the Stefan-Boltzmann constant. If you see on those in yellow at the top there, we find that A is the geometric albedo, the A that we calculated just before, and then we have L, capital L, which is the star's luminosity, or the sun's luminosity in this case, because Jupiter is orbiting the sun, and we see that the sun is the star. In this case, the sun is a star actually in this case. So we are looking at the luminosity of the sun, which is around 3.8 something if you look at the value there, which is in watts. And then we have the sigma, the small letter sigma in the Greek letter, which is the Stefan-Boltzmann constant, which is around 5.67 blah 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 watts. We'll find that it's times 10 to the power negative 8 watts by meters squared by kelvins to the power of 4. Yes, so that's the unit. It's a very long unit, it takes time to read, so bear with me. Okay, so our last thing will be same major axis, which we're going to be using as well, which in this case we've put as Z. I think most cases we use Z instead of A. We don't want to confuse that albedo and area. And by the way, if anyone knows the definition of a black body, this black body temperature, just put it in the comment section so that we get to understand. I'm not quite good at explaining it, so we'll just have to continue and not waste time. But if you understand, just put the definition in the comment section, or just explain to everyone so that we get to understand this thing. But it's very easy to calculate, don't worry. We have T is our temperature, which is the value that wasn't stated there. That's the unknown which we're trying to calculate. It is the black body temperature. That's our T. Like I said, we have the gray body temperature and all these other temperatures. So we find that's the expression there. T is equal to the fourth root of 3.928 by 10 to the power of 26 watts, which is the luminosity of the sun, which is our star in this case, multiplied by 1 minus the geometric albedo, which we calculated, which was 0.5175, over, in the denominator we have 16 pi multiplied by the Stefan-Boltzmann constant. I won't read it, it's that value, and then we'll multiply that with the same major axis squared. In our same major axis we put it in meters, because remember the SI units rule, we put the SI units when we're calculating, so we have to convert it to meters, which is around by 10 to the power of 9, and then we have to square that, 778.479 by 10 to the power of 9 squared. Remember, it was gigameters. Those values were gigameters, so that's why we put 9 to the power of 9. And then we say that will be equal to 101.68 blah 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 kelvins, which is 101.7 kelvins to 1 decimal place. Usually for temperature and angles, we put them to 1 decimal place. But according to the NASA Jupiter fact sheet, which you can find on the internet, I think I'll put the link in the description for the YouTube viewers. It states that T will be equal to 109.9 kelvins instead of 101.7. So if you can see where the error is, which I suspect that error that area is coming from the albedo part. That's why that's what I'm thinking. But if you can understand where the area is coming from, please assist us in the comment section. Yeah, so to convert it to degrees Celsius, I think you subtract 273 kelvins, approximately that, but it should be around 273.16, which is the value for the thermodynamic temperature. But for the absolute zero, where we have absolute zero of temperature, it's around 273.16, around there in the negative. So if you subtract that value from 101.7 or 109.9 kelvins, you should get the value in degrees Celsius for the temperature of the black body. But usually here we use thermodynamic temperature, which usually puts in kelvins. That's why you see it like that. So I think we're done with this calculation segment. I wanted to put a graph, but I think now that you know statistics, after that statistics video that I pointed out to and cited in my MS video, you might also have to use it there to draw the histogram or the graph, whatever you are going to. I am not going to tell you what you're going to how you're going to present it. You can present it the way you want, but you have to show the different gravities of different planets. You're going to see something interesting with Jupiter's gravity, because it is a very large body in the solar system, not larger than the sun, but it's still large. You're going to see something very interesting amongst the planets concerning gravity. The size of the gravity on Jupiter is somehow very great because of that mass that is also big. Maybe you can try and explain why it is like that. And yeah, hopefully you get to enjoy finding out how much gravity is on Jupiter after your calculations and representation of that data that you're going to be calculating for all the gravities of the other planets. I think we are now done. Enjoy the rest of the video as you get to know more about Jupiter. Cheers. More on Jupiter. Jovian environment.